So here's an example of an axial member where both the internal normal force and the cross-sectional area vary across the length of the member. Here we have a column with 3 discrete sections. It's column A, B, C, D. Between A and B, it's 50 inches long. All of these are round cross sections, and they're all made out of copper as well too. Section AB has a diameter of 3 inches. It's 50 inches long. Section BC has a diameter of 2 inches. It's 75 inches long. Section CD has a diameter of 1 inch, and it's 60 inches long. And we can see that there are various external loads applied. Again, don't be tricked into just plugging these values into our equations for the change in length. We need to go from external loads here to internal loads, and we'll go through that process as well. So all that we're trying to find here is the overall change in length of between points A and D. So the overall change in length of the entire column is what we are trying to find. So I'll put a question mark here. So we need to go back, and we always want to write down the fundamental equation that governs the problem that we're going to be working on. And here our general equation for the change in length of an axial member is the integral over the entire length of the internal normal force times dx divided by the cross-sectional area as a function of x times the modulus of elasticity. So this is the general form equation. It always works, but we can often simplify it down. We've already tabulated some of the simplified versions of this. So here we don't need to use the integration because we can simply look at this as 3 independent columns, and we'll add up all of the deflections of each column together. And so we'll treat A to B as its own individual column. And because our external loads are only applied to the ends of that column, the internal normal force is going to be constant the entire length from A to B. We'll verify that with a free body diagram, but each of these has a constant cross-sectional area because the diameter is constant, and as well as a constant internal normal force because we only have loads applied at the end. So the form of this general equation that we can use gets a bit more user-friendly. And it's simply the overall deflection of this column is going to be equal to the summation of the deflections of each section, because each section has a constant normal force and a constant cross-sectional area. It just becomes a summation of N L over AE. This is the equation that we're going to want to use. And so just to break it down and make it a little bit easier to understand, the overall deformation will be equal to the deformation of member AB plus the deformation of member BC plus the deformation of member CD. And I could rewrite that a little bit more verbosely. I'd have NL over AE for member AB. I will have NL over AE for member BC. And I will have NL over AE for member CD. Each of those we treat as just an individual column. So it might be helpful to make a little table, and actually I kind of have one started here. I want to tabulate N, L, A, and E for each section, and I can kind of start that right here. This first entry is the length. We also need to keep track of the cross-sectional area. We'll calculate that in a minute. I need to keep track of the internal normal force as well too. We'll calculate that in a minute as well. And we also need to keep track of the modulus of elasticity, E. And again, this is member AB, this is member BC, and this is member CD. So if I keep track of all of these, the actual change in length, the delta for each section, is just a very basic arithmetic operation with L, A, N, and E. And so I need to fill in each of these other 3 rows right here, then I can calculate delta. And then the total delta is just equal to the summation of all of those together, and that'll be our final answer. So it might be helpful to organize your results like this when we have what I would call a piecewise column. A column is an assembly of multiple smaller columns. So here L is already given to us. A is going to be really straightforward because we have, we're told that this is a round, a circular cross section, and we're given the diameters. So I could just write down the equation that A for a circle is equal to pi divided by 4 times the diameter squared. And so in this case, pi over 4 times 3 inches squared, we get 7.07 square inches. Pi over 4 times 2 inches squared, we get 3.14 square inches, is pi square inches. And for the 1 inch diameter, we get a cross-sectional area of 0.79 square inches. All right, I'm going to skip the internal normal force for now. We'll do some diagrams of that in a second. But the modulus of elasticity. So that's kind of like the material component to stiffness, whereas the cross-sectional area is the geometric component of stiffness. The modulus of elasticity is how the material contributes to the resistance to deformation. And here we're told that this is all made out of copper. I mean, it would be fair game for all of these to be different materials, but here it's copper the entire way from A to D. And so all that we would need to do is look up in the back of your textbook, or if it was on an exam, it would be given to you what the modulus of elasticity of copper is. And if you look in the back of your book, we will find the modulus of elasticity of copper is 18,000 KSI. 18,000 kips per square inch. And that's the same for all of these because they're all the same material. All right, that's just found in the back of the book. It's just a reference number. Okay, so now before we can calculate delta, which is simply equal to NL over AE, we need to calculate the internal normal forces for each of these sections. And so it's just statics to go from the external loading to the internal resultants. And so all I'm going to do is make 3 different section cuts here. So I'll make a section cut here, section cut here, and a section cut here, and I'll analyze each of those individually. And so the first section cut, the section cut between A and B. So note that it doesn't really matter how close I am to A or how close I am to B. There's no loads between those points, so whether I make a section cut close to A or close to B, the relative forces are still going to be the same. And so if I make my free body diagram, I can choose to keep everything to the right of the section cut, or I can keep everything to the left of the section cut. Here, it's easier to keep everything to the left because we only have to deal with one external load. And so my free body diagram, I have a portion of member AB up until the section cut, and this is point A right there. So we're looking for the internal normal force, and I would advise you to just draw the internal normal force in the assumed direction before you even consider drawing the external loads here. So that's because we want to always follow the sign convention for the internal loads. And the sign convention is that the internal normal force points away from the section cut, and that means away from the section cut for this free body diagram would be to the right. This would be our internal normal force for member AB. So now I'll draw the external load, which is this 6 kips pointed to the left. It turns out that that's going to be the correctly assumed direction, but it wouldn't have been a big deal if we got a negative value for NAB, because it's critical that our positive values correspond to tension and our negative values correspond to compression, because when we add the results together, we don't want to say that compression and tension add up together because they actually cancel each other out, and we'll see that in this example in just a minute. So here I will use the same coordinate system for all of my equations of equilibrium. I'll draw that right there. Now if I sum the forces in the x equal to 0, I will get 6 to the left, which is minus 6 kips, plus n, because it's going to the right, equals 0. Rearrange that, I get that the internal normal force between points A and B is equal to positive 6 kips. Which makes sense. You can tell that AB is going to be in tension. We're pulling on it. It's got to be in tension. Okay, so member BC is a little trickier. Well, not really too much trickier. We make our section cut, and then we get to choose either side to keep for our free body diagram. It doesn't matter which side you choose. You'll still get the same answer as long as you follow the sign convention. So for member BC, I'm going to keep everything to the left of the section cut, but again, it's arbitrary which side you choose. In this case, it's really the same amount of forces, same amount of locations. And so I have member AB, and I have some small portion of member BC, and then I have my section cut. So this is point A, this is point B. And just like before, I want to draw my internal normal force before I start putting on my external loads. And so here, my internal normal force, I assume it's pointed away from the section cut. So this is the normal force in member BC. Now I'll draw on my external loads. I have 6 kips at A. I have two kip forces being applied at B. And I have the same coordinate system. So now if I want to find NBC, I just sum the forces in the x equal to 0, and I get minus 6 kips plus 2 times 2 kips, so plus 4 kips, plus the internal normal force in member BC is all equal to 0. So if I rearrange this, I get that the normal force in member BC, isolated by itself on one side, is equal to positive 2 kips. And so I get positive 2 kips. Finally, I need to find the internal normal force in member CD right here. I've made my section cut shown in green. I can choose either side of that I want. I'm going to keep everything to the right because I only have one force to deal with. And that'll also illustrate the sign convention that we've talked about before. So here for member CD, I keep everything to the right of the section cut. Here's my actual section cut. And now I want to draw my internal normal force. Sorry, this is point D out here to the right. When I draw my internal normal force in member CD, I draw it following our sign convention, which says that you always draw the internal normal force away from the section cut from the portion of the beam that remains. In this case, that will be to the left. That's normal force in member CD. Now I'll draw my externally applied loads. And all that we have here is a 1 kip force at point D pointed to the left. So if I want to find NCD, all that I do is sum the forces in the x direction equal to 0. I get minus CD minus 1 kip equals 0. Add NCD to either side, and I get NCD equals negative 1 kip. Okay, so members AB and BC were positive, they were in tension. Member CD is in compression, is in 1 kip of compression. And we got to that because we followed our sign convention. And you can tell here 1 kip pushing in on the end, it's got to be in compression. So it kind of passes the reasonableness check. So now I have everything in my table that I need. I need to double check that everything is in the right unit system. Here I have inches, inches squared, kips, kips and inches. So everything's in kips and inches, so we don't need to make any sort of unit conversion, so we're okay there. So all that I'm going to do now is calculate delta, the change in length of each of these members individually using NL over AE. And then I'm going to sum up all of the results down here. I'm going to sum up NL over AE each of these cells right there, and that'll give me the total deflection of the entire assembly. And so here, NL over AE for member AB is positive 0.0023574 inches. For member BC, it's positive 0.0026539 inches. And member CD is minus negative or compression contraction 0.004219 inches. So I added some additional significant figures in here because it ends up that the positives are actually pretty close to the negatives. And so to get enough significant digits for the final answer, I had to extend it out a little bit. And what we end up with is that when I add all of these together, these two add up, this one takes away from it, and I get the total deflection is still positive, but a very small magnitude. I get 7.92 times 10 to the negative fourth inches. That's the total change in length of the assembly. And remember, signs are very important because these two are making it longer, this one's making it shorter, and you superimpose all of the results together.